Hi guys, so I'm going to go over chapter 7 practice. I'm going to do just a couple of those problems to help you guys out so you can kind of see the motion of how these problems are solved. All right, so let's go ahead and get started. Now, I'm going to turn this off because looking at myself distracts me. Okay, so the first part is we want to calculate the formula mass of barium sulfate. And if we recall, in order to calculate the formula mass of anything, we're going to need a periodic table. So I'm going to look at the table. Boom, boom, boom. And I have a periodic table here now. So I'm going to look for barium. Okay, let's see if we find barium. Barium is going to be right here. It's in group 2, and it has a formula mass of 137.33. So barium is 137.33 atomic mass units, AMUs. Then we're going to look for sulfur. Sulfur is 32.06 AMUs, atomic mass units. And then we have oxygen. Oxygen, right above it, is 15.9999, so we're just going to round that one to 16. However, there is 4 of them, so we're going to multiply that 16 by 4. And just because I don't want to mess up on my math, I'm going to use the calculator, and we get 64. Okay. So to calculate the formula mass of all of these, I'm going to simply add them up together. So the formula mass of barium sulfate is 137.33 plus 32.06 plus 64. So we're going to go ahead and add all of these up together, and that plus 137.33 plus 32.06, and we get 233.39. 233.39 atomic mass units, or I prefer grams per mole. It's better to get accustomed to doing grams per mole, but just note that grams per mole is the same as your AMU, your atomic mass unit. All right, next one is, what is the percent of mass by oxygen in sodium nitrate? So we're looking for percent. Your percent is going to be the part over the whole. So what are you looking for over the entire thing, right? So in this case, our part is going to be the mass of oxygen, and I'm just going to write the whole thing out. And then the whole is going to be mass of sodium nitrate. Well, in order to be able to do this problem, we actually have to figure out the chemical formula for sodium nitrate. Sodium is Na, and nitrate is NO3. Sodium makes a +1 charge, and nitrate makes a -1 charge, so they combine together in a 1:1 ratio. So now I could rewrite this. I'm looking for oxygen. I have 3 oxygens, so I need the mass of 3 oxygens over the mass of NaNO3. Okay. Now I could go ahead and look. Oxygen is 16, so I'm going to take 16 times 3, and that's going to give me 48. So I'm going to have 48 on the top over the mass of this, so that's going to be 16 plus nitrogen, which is 14.007, plus sodium, which is 22.990. And get 84.997. 48 divided by 84.997. 0.997 is equal to 0.56 something times 100. I get, so let's actually put the times 100 because we're looking for a percent. We get 56.47%. So I'm just going to put 56.5%. So that's what this means. That means that we have this much oxygen inside of nitrate, sodium nitrate. So majority of sodium nitrate is oxygen. It's over 50% of it, of oxygen. In our sodium nitrate. Okay. All right, next part, connecting atomic mass to large scale mass. We're going to be talking about the mole concept. So we're just going to be converting. Using our conversion factors, we could either go from moles to grams or grams to moles. And what we use here is we're going to use the formula mass from periodic table. All right, so we want to go from grams to moles. So we're going to convert these to moles. Always start with your given. So always start with given. My given is 3.21 grams of iron. Now I want to go ahead and convert that into moles of iron. Okay, so swing, bring the grams of iron down, and I want moles, so moles of iron go on top. In 1 mole of iron, there is, let's figure out how many grams. 55.845 grams. Okay, so 3.21 divided by 55.845 gives me 0.057, and that 8 rounds up that 4 because I need 3 sig figs to a 5, and the answer is going to be of what? Of moles of iron. Okay, so make sure your answer has the correct sig fig, and you tell me your unit is, what you're looking for, and of what. What is it that you have? So we started with the given. We identified the conversion we needed. Okay. We made sure that our units canceled out. Solve the problem, and then give answer in correct sig figs. So in correct significant figures, unit, and of what? Which molecule or atom of what? All right, so let's go ahead and go into another one. Let's do this one down here. Convert the following from moles to grams. So now we're going to be doing the opposite. So starting with our given again, moles of copper. Bring this unit down. Shing! Mole of copper at the bottom. We want grams, so grams goes on top, grams of copper. Okay. In 1 mole of copper, there is 63.546 grams of copper. All right, that comes directly from the periodic table. Okay, I'm just going to multiply these two together. And I get 469.6 grams of copper. Now, the 0.6 is actually going to round up that 469. So we're going to get 470. Oh, you can't really see that, huh? 470 grams of copper as our final answer with the decimal at the end. The decimal at the end is to show that we understand we need 3 significant figures. Convert the following from particles to moles. So now we're going to be using Avogadro's number. So these two were the periodic table. Now we're going to use Avogadro's number because it says the word particles. And Avogadro's numbers deals with particles, atoms, molecules, those kind of things. Okay. So we have 5.93 times 10 to the 26. Bring the unit down. The unit is atoms. Okay, so atoms. It's using atoms. See how this said particles and this one says atoms and this one says molecules? It's to help you understand that it's the same thing, right? They're all different, but when it comes to Avogadro's number, it doesn't matter if you're talking about atoms, molecules, or particles. Okay, so we brought atoms down and we're going to have the 1 mole on top. The number of atoms is going to be Avogadro's number, 6.02 times 10 to the 23rd. Atoms cancels out with atoms. Now we're left with this little problem to solve. I'm going to hit my handy dandy calculator. And we have 5.93 to the 26th power divided by 6.02 to the 23rd power. And that's going to give me 985 moles of zinc. So in that many atoms, I have 985 moles of zinc. All right. Let's go into this one. Now we're going to convert from moles to atoms. We want to know the number of atoms. So it's the reverse process. 55.3 moles of titanium. Now, I don't remember the symbol for titanium. Ti, there it is. Ti. Okay, bring that unit down. Shwing! 1 mole of titanium. Using Avogadro's number. You just use it. That's the beautiful thing about the ones involving Avogadro's number is that number is not going to change. It's either going to divide by it or multiply it by it, but it's not going to change. You're not going to be like, just like we did for these ones where the number changes because of the molar mass on the periodic table. These do not change. It's just going to be Avogadro's number as your conversion factor. Okay. Now we get to solve for the number of atoms. And we have 55.3 times 6.02 to the 23rd power. And we get 3.33 times 10 to the 25th power. So as you can see right here, that 9 rounds up the 2. Ten to the 25th power, and this is the number of atoms of titanium, Ti. How many atoms are in 5.05 gram sample of iron? All right, this is actually a good question. I love these questions because it involves more than one step. So let's look at this mole concept map and see what are the steps that we need to take to solve it. We are given a gram, right? Not a gram, we're given 5 grams. But here we are, we're given grams. So grams is right here. It doesn't want moles. It wants atoms, which is the same as our particles. So we have to go from here to here, and then from here to here. Okay, it's like a bus that wants to take you somewhere, but it has to stop at the station first, and then you get on another bus, and it takes you to a different station. Or plane, whichever one. Okay, so we have to convert from grams to moles, and then from moles to our atoms. So it's a little process right there, but nothing we can't handle. So we have grams of iron, and we're going to convert our grams of iron into moles of iron by using the molar mass. Okay, bring that unit down, grams of iron at the bottom, 1 mole of iron on the top. Iron has a mass of 55.845. 5.845. So that allows grams to cancel out and I get moles. And from moles, I could go into atoms by using Avogadro's number. So bring this unit down. 1 mole of iron, 6.02 times 10 to the 23rd atoms. Okay. And now moles of iron cancel out. And we're left with this little problem here. And it's nothing that we can't handle. All it is this divided by that, and then you multiply it by that. So let's go ahead and do that. 5.05 divided by 55.845 times Avogadro's number, and we get 5.44 to the 22nd power. So 5.44 times 10 to the 22nd, and this is the number of atoms of iron present in 5 grams, right? Present in 5.05 grams of iron. Okay, so those problems aren't anything difficult. It's literally just putting your things together. Realize how in the unit, I always bring the unit down, so that allows me to easily figure out what I need to use, like as a conversion factor, right? So sometimes we get confused and we're like, oh, what unit do I do? Well, here, bring the unit down, then this part that you want, like this one we want it moles, that one on top. Bring the unit down, the part that we want, atoms, goes on the top. Okay, let's see what we have on the other page. So now we're going to have a limiting reagents kind of problem, I believe. Let's take a look. So it says, consider the following generic reaction. 3A plus B gives you 2C. If a chemist carries out this reaction using 11 moles of A, how many moles of B are needed? How many moles of C can form? All right, so it's a limiting reagent equation that we're going to solve. So to solve it, let's go ahead and do this. So we have 11 moles of A, and we want to know how many moles of B. And actually, it's simpler than a limiting reagent. I don't know why I said that. It's just a mole-to-mole conversion. We're literally doing a mole-to-mole conversion now. We're going to go from mole of A to mole of B, and we're just going to use the mole ratio from the equation. Much simpler. Okay, much simpler. Okay. These are our mole ratios. They're the coefficients, and there's a 1 right here. Remember, when you don't see a number, it's a 1. Okay, so we're going to turn moles of A into moles of B. So we're going to take this, bring this unit down. Shwing! Mole of A on top, mole of A on the bottom, mole of what we want on the top. So let's take a look at this. We have 3 moles of A, and we have 1 mole of B. So we're going to have 11 divided by 3 as our answer. And that gives me 3.67. 3.67 moles of B. And you're going to do the exact same thing, but you're going to look for moles of C. So this one is going to represent your moles of C, which are right here. Okay, next question. Potassium reacts with water according to the balanced chemical equation. The equation is shown. If 1 mole of potassium reacts in this manner, how many moles of water are consumed? So we're going to go from, let's see, the equation, figuring out 1 mole to 1 mole of potassium to moles of water. Then we're going to figure out how many moles of hydrogen, how many moles of potassium if we had 14 moles of hydrogen, and how many moles of potassium hydroxide being produced if we had this many moles of H2O. All right, so super simple questions. They're just kind of jumbled up all together. Let's see if we have some space here to answer them. So A says if you have 1 mole of potassium, so that means that's my given, 1 mole of potassium, how many moles of water are consumed? Well, I'm going to use the mole to mole ratio, and we'll notice that you have 2 and 2 as our ratio. So you have 2 mole of, what are we looking for, water, over 2 mole of potassium, which is basically going to cancel out moles of potassium and give you 2 moles of water. Okay. All right, let's look at B. Oh, I don't know why I said 2 moles. 1 mole of water. 1 mole of water. The 2 and the 2 cancel out, so we get 1 mole of water. All right. B, if 1 mole of potassium reacts in this manner, how many moles of H2 are going to form? Okay, so 1 mole of potassium, and now we're going to look for dihydrogen. It's right here. It has a 1 as a ratio, so 1 mole of hydrogen and 2 moles of potassium, because this still has not changed. We take our handy dandy calculator. Basically, it's just 1/2. 1/2 is the same as 0.5 moles of H2. C says how many moles of potassium are required to produce 14 moles of H2. So now we're going to start with 14.0 moles of H2. And we're going to bring this unit down. Shwing! So we have moles of hydrogen right there at the bottom. And we want to know moles of potassium. So we're looking for moles of potassium. Mole of potassium goes on top. I have 2 moles of potassium. And I have 1 mole of dihydrogen. So I'm left with 14 multiplied by 2, which is going to equal 28 moles of potassium. And lastly, we want to know how many moles of potassium hydroxide would be present if 3014.2 moles of hydrogen are consumed. Okay, let's see, do we want to do this one? Yeah, let's go ahead and do it. Okay, so you get 3,014.2 moles of H2O. And we're going to do our mole to mole ratio, bring this unit down. So that's moles of H2O, moles of KOH, and we have 2 moles of each according to our equation. So moles of H2O cancel out, and we're left with moles of, which one's KOH. Okay, we're going to go ahead and solve the problem. And as we solve the problem, 2 over 2 cancel out. We're just left with 3,014.2 moles of KOH. Okay, now we have just a few more to do. Alright, guys, so let's look at number 10 and what are the steps that you have to do for number 10. So it says copper 1 bromide reacts with magnesium metal. So here's our equation. Copper bromide plus magnesium produces copper and magnesium bromide. If 0.253 moles of magnesium react in this way, how many grams of copper bromide, how many grams of copper, and how many grams of magnesium bromide are produced and or consumed? So we're literally going from moles. So this is the steps we're going to take. We're going to go from moles of A to moles of B to grams of B, grams of the second thing. Okay, so in this case, this is your moles of A, right? This is your moles of A. And now we're going to be looking for grams of B. In A, grams of B is copper bromide. In this one, it's just copper. In this one, it's magnesium bromide. So remember, in this step here, you have to use the coefficients, your molar coefficients from the balanced chemical equation. And in this step here, you're going to use your molar mass from the periodic table. Okay. All right, let's look at number 11. 11 says, consider the following generic reaction. A chemist carries out this reaction using 8 moles of A and 3 moles of B. What is the limiting reagent in the reaction, and how many moles of C can you form from this reaction? So let's go ahead and do this one since it's a limiting reaction one. Okay. We're going to first start off with our 8 moles of A. So we have 8 moles of A and 3 moles of B. And we want to figure out what is the limiting reaction. So what this means, this is a 2 steps or 2 equations that we have to do. Equation using moles of A and equation using moles of B, and seeing which one produces less, right? So I'm going to see if I can divide this actually. Let's divide this right here. So let's go with A. First part is 8 moles of A. Right? And we're going to do a mole-to-mole ratio and figure out, well, what is the limiting reagent in this reaction for, I believe it said C, right? For C. Okay. So let's go ahead and do our mole-to-mole ratio and figure out, well, how much of C we're going to produce. So here's C. And moles of A goes at the bottom. Moles of C, which is what we're looking for, goes on the top. We have 3 moles of A for every 1 mole of C. So then we're left with 8 divided by 3, and we get 2.67. Okay, so we get 2.67, or let's just round it to 2.7 because we're given 2 significant figures right here. So 2.7 moles of C. As you notice, we don't even need to have an element for this one since it's just a mole-to-mole conversion, and that recipe is given to us right here in this balanced chemical equation. All right, let's go ahead and do the next part using the other mole value, which is 3.0 moles of B. And we're going to do the mole-to-mole conversion, bring moles of B to the bottom and a mole of C to the top. We still have 1 mole of C and 1 mole of B. So this provides us with 3.0 moles of C. Okay. So the limiting reagent in the reaction is going to be A. So 8.0 moles of A is the limiting reagent. Let's move this out of the way here. Okay, now let's look at the next question. How many moles of C can form from this reaction? We can form or produce 2.7 moles of C from the reaction. Number 12 says potassium reacts aggressively with water as shown in the equation. What mass of potassium hydroxide can form from this reaction? We have to figure out, well, which one is the limiting reagent? Is it going to be potassium or is it going to be water, right? So that's going to be the first step. In order to figure out which one's the limiting reagent, since we are given in grams, you're going to have to convert your grams to moles. So convert grams to moles. So I'm going to write down the steps, and then you guys could try this one out on your own and see how you did with the limiting reagent. So this first step is convert grams to moles. So you're going to turn this into moles, and then you're going to turn that into moles. You're going to do the same two processes here using this balanced chemical equation there. So you're going to have one for potassium and one for water. So convert grams to moles. Then you want to convert moles of A to moles of B. All right, last one is theoretical and percent yield. A chemist carries out the following reaction. If he reacts 14.2 grams of C6H6 with an excess bromine or bromide, what is the theoretical yield of C6H5Br? Okay, so here is our equation. This is how much he reacts. And he says bromine's in excess, and we want to know the theoretical yield that can possibly be produced from this. Now remember, every time you hear something is in excess, that means don't worry about it. Cancel off, whatever, it's gone. I don't care, right? We have so much of it that we're not even bothered to know like what it's going to produce because there's too much of it. So therefore, our C6H6 is going to be our limiting reagent. Okay, so this one's our limiting reagent. All right, so we're going to react this, and we want to know what this is. So we're going to go from grams of A all the way to C6H5, so grams of B. So in order to do that, we're going to go from grams of A to moles of A to grams of B. Oh, sorry, to moles of B. I'm already jumping ahead. Moles of B to grams of B. Okay, we're going to follow that process. So this part and this part is using molar mass of A. This part to this part is using the molar coefficients based on this chemical equation. We were going to just verify that it's balanced before doing anything because it doesn't say the equation is balanced. So you need to verify that it's balanced. All right, and then moles of B to grams of B is going to use the molar mass of B. All right, let's go ahead and verify just because 6 carbons, 6 carbons, 6 hydrogens. We have 5 here and 1 here. That's 6. 2 bromines, 1, 2, 2 bromines. So it's all a 1-to-1 ratio, and that's good, right? So if we start here, we're going to have 14.2 grams of A, and I am going to bring this unit down, grams of A over 1 mole of A. What I want goes on top. I'm going to continue setting up my problem. Mole of A in the bottom, mole of what I want on the top. This is what I want. The next step is bring this one to the bottom, mole of B, and then what I want, grams of B on the top. Now I'm using A and B just to make it a lot faster for me. Okay, C6H6, that's 12 times 6 plus 6. That's going to give me about 78.12 grams per mole, atomic mass units for the formula mass there. And this one right here, we have 12 times 6 plus 1.01 times 5. Okay. And this one is going to be 157.01 grams. I got these numbers by looking at the periodic table. So it's grams per mole. So all I did was the formula mass for them. Okay. So these numbers I'm now going to plug in. So this one is 78.12. And this number for B is 157.01. The mole to mole ratio, they're all 1-to-1. So I'm just going to write 1-to-1. I'm going to solve this problem. The units are going to cancel out. Mole B. I'm left with grams of B. That's what I want. So I'm going to have 14.2 divided by 78.12 times 157.01, and I get 28.5 grams of C6H5Br. So this is the theoretical yield. Theoretical yield. That means how much can I possibly produce? I could possibly produce up to 28.5 grams. Now, when we conducted the experiments, we isolated this much, okay? We isolated 16.3 grams of the 28 possible grams. What is the percent yield? This is going to be part over whole. So this is A, and I'm going to have B right here. So percent yield is the part over the whole times 100. So, or the actual over the theoretical, right? I actually produced 16.3 grams, and I theoretically could have produced 28.5 grams, and I multiply that by 100. So that's going to be 16.3 divided by 28.5. The grams units cancel out. I multiplied them by 100, and I am left with 57.19 something something. So it's just going to be 57.2%. That is how much I actually produced, how much I made of what I could have possibly made. So less than 60%. All right, you guys, hopefully this helps you guys out. Try them out your own. Try the ones that I didn't do, and refer to the set to help you out, or email me if you have any other issues. This roadmap is very essential in helping us and figuring out how to solve problems. All right, you guys, take care.